Everyone can see my slides fairly well. Sorry about the thing on the top left there, but if that is the case, then good morning to folks in the US and good afternoon to folks in Europe and probably good evening everywhere else. My name is Micheal Simpson, and today I'm going to be presenting work that has been conducted by myself and as well as my fellow colleague Andrew Osborne on implementing deep learning machine learning techniques for radar QPE. So for this presentation, I'm going to be presenting some results that we have established thus far and the problems and issues that we have faced and issues that are still ongoing. And so as a real basic introduction in the United States, so in general, as meteorologists, as most of us are aware of the fact that severe weather incorporates a multitude of different phenomena ranging from tornadoes, hail, flash flooding, winter weather, fire weather, and among others that are on the slide. However, not all of us may be completely aware of the fact that the vast majority of fatalities and costs due to natural hazards, at least in the US, are due primarily from flood-related events. So this slide simply demonstrates the importance in not only research-related interests to flood-related events, but also how important it is for stakeholders, the public, and everyone else to just understand just how catastrophic these severe weather events are related to severe flooding. So in order to accurately estimate precipitation, one needs a system that is capable of measuring high spatiotemporal resolutions. So one such system is the multi-radar multi-sensor, or MRMS suite of products, which produce results every 2 minutes on a domain of 1 kilometer. And so this system of products incorporates data from radar, satellite, model, gauge, and lightning data. And so because of the large demand of products from stakeholders due to the accuracy and resolution of MRMS products, a large volume of data are generated basically every day, which are then validated against extensive gauge networks for quality control techniques and also measurements. However, with all of this data, it's generally impossible for a single human or even a couple group of people to sift through everything. So with the recent interest in machine learning technology and the explosion within specifically the meteorological realm, the data that is available from the MRMS suite of products provides a unique opportunity to leverage AI and ML technology to test against current operational, physically based quantitative precipitation estimates, or QPEs. So this presentation will present some results based on single radar data, as well as the Mosaic product suite. So for single radar data, a polarimetric S-band radar in the northern section of Taiwan, RCWF, was utilized for this initial pilot study. So although Taiwan has a large number of radars and has a very dense gauge network, which is displayed on this image to the left, one radar is nearly capable of covering almost the entire island. And so the radar range rings are presented on the right-hand side. However, as the image also portrays, the central mountain range dominates the majority of the eastern half of Taiwan, resulting in complex microphysical processes that are, in general, too difficult for physically based methods of QPE or even model data to explicitly resolve. Thus, the question is, can machine learning help in improving QPEs over Taiwan? So in general, how was the machine learning data set up? And so in general, the first step was to match the latitude and longitude of each gauge location with a corresponding radar pixel or gate, depending on which terminology you prefer. So therefore, we have an overlap between the point-based ground truth gauge data as well as the aerial-based input variables, which from this pilot study were reflectivity, or Z, ZDR, KDP, and rho HV. So within an arbitrarily defined 250 kilometers from the RCWF radar domain, a total of 267 gauges were utilized as the ground truth. So 250 kilometers keeps things rather constrained so that we don't have too many issues from either overshooting of the beam or melting layer potential issues. So the ground truth gauges were on a 1 hour temporal resolution. And so to match this 1 hour resolution, the volume scans from the radar were accumulated for each variable that was listed above. And so overall, now we have a 1 hour ground truth data set, and now we have a 1 hour accumulated variable that goes into the machine learning model. And so for this initial study, there were 18 days chosen for analysis, and we can see that if we have a 5x5 grid over this ground truth data set, the amount of data that's available for each variable, it very quickly becomes a large number, where with just each variable, even for only 18 days, we have over 17 million observations. And so as we start to expand upon this, we can see that the numbers will exponentially increase very quickly and very rapidly. And so I just kind of wanted to also present a very brief overview of the CNN architecture as well too. There's really nothing exceptionally fancy about the model. It's a relatively basic CNN model with one convolution pooling layer with 64 convolutional channels with a dropout that's rather aggressive of 50%, with the typical atom optimizer with 3 dense layers. And it was found through a bit of optimization that about 150 epochs are necessary for this data, with a batch size of 1,000, which takes only about 5 minutes per simulation to run. And so these are the initial results from the single radar-based hourly QPE values from the machine learning model. And so from left to right, it's demonstrated the improvements in the machine learning model based on the addition of more polarized variables to the analyses. So for example, the correlation coefficient values, hopefully everyone can read that. If you go from left to right, as we add in more polarized variables to the model, the correlation coefficient values tend to increase, and the mean absolute error, or the MAE value, tends to decrease. And so the scatter plots show the hourly gauge value along the x-axis, and the machine learning estimated hourly precipitation values along the y-axis. And so these are just the 2D generated grids of the QPE that was generated from the machine learning model for each of the variables that have been added sequentially into the model performance. And so we'll also have another video on this slide where this slide demonstrates the performance between the machine learning based hourly QPE on the left-hand side versus the physically based QPE algorithm on the right-hand side for Taiwan. So similar to the previous slide, we have the gauge value on the x-axis, and then we have the hourly QPE value on the y-axis. And so I'm just going to let this sort of slide through one more time so we can sort of see the similarities between the two machine learning models in terms of the machine learning model as well as the physically based model in terms of general structure, the extent of the QPE, and in general things seem to match up very similarly, but there tends to be a bit more compactness along the one-to-one line for the machine learning results for this initial pilot study. And so with the promising results from Taiwan, a similar setup was established for the United States, where it was particularly focused on the West Coast, where, again, complex terrain and especially radar gap coverages tend to result in decreased performances in the QPE. So there are more variables available for the CONUS. So, for example, we have more information about the radar beam height, surface temperature, and other models. And so if you would like to kind of know more about this complete list of variables, just feel free to ask a question in the chat, or you can feel free to email me. But it should also be noted that for these simulations that are going to follow, the presentation is that of 24-hour accumulations. So as with Taiwan, those were all hourly accumulations of QPE, whereas for these, there are going to be 24-hour accumulations, just simply adding each individual 1 hour to get a 24-hour accumulation. So these are some initial results from the physically based model over Western California. And so we can see that the physically based algorithm that there is, in general, an underestimate in the precipitation values marked by most of the red dots. And again, on the left-hand side, we have the gauge values on the x-axis, and then the physically based QPE values on the y-axis. Now, if we switch to the machine learning model, we have a bit of the opposite effect, where a lot of the underestimates are dramatically improved, but we do have a bit more of overestimates. But if we sort of toggle back and forth, just a slight little bit, we can see that there is, in general, improvements, but there is a tiny bit of overestimation with the machine learning model based in California. But if we take a little bit further zooming out, a similar story is kind of observed, where there are, in general, many underestimates outside of the San Joaquin Valley, which is centered pretty much in the state of California for this physically based algorithm, whereas things tend to improve quite a bit, especially on the eastern side of the San Joaquin Valley, where we typically see a little bit more overestimates. And if we move back and forth a tiny bit between the two slides, we can see that in general, things tend to line up more with the one-to-one line quite a bit better. But again, we are starting to see a little bit more overestimates as the underestimates are improved. And we'll just kind of show one more example from another case as well, where there is in general a bit more increase of the precipitation range from the machine learning model, which improves the correlation coefficient values, the root mean square error values go down, and overall statistical performances have improved based on the machine learning model. And if we move to the island of Hawaii, in general, there's not going to be as many gauges available because of just in general the size of Hawaii. However, we can get a general idea as to the performance of the machine learning model compared to the physically based model. So if we have this as the physically based model, again, we start to see a little bit more improvement in terms of the QPEs in terms of at least overestimates here. And we can see a slight bit of, I don't know if everyone can see my mouse here, but in general, there are a few artifacts that are picked up in the machine learning model, which are more highlighted if we move to the next case, which we can see significant blockage from the mountains that is inherent within the island of Hawaii. But when we start looking at more cases such as this, the machine learning model does tend to provide quite a bit of improvement on the precipitation estimates if we kind of toggle back and forth between the physically based and the machine learning based. And kind of to wrap things up before I go over a bit of time, and so we have quite a bit of different machine learning models that are available for analysis. So we have expanded upon the CNN model to implement long short-term memory, or LSTM. And so this general setup was a little bit different, such that the training data consisted of areas across the entire CONUS, and then certain areas were tested for the simulation data sets. And for this data, because we have a lot more available to us, only 8 variables were utilized instead of the 13 and 20 that were used for the CNN on the previous slides. And so this is just going to be a 1-hour simulation from the middle of Oklahoma, where the physically based algorithm shows relatively good results overall, and the machine learning model indicates that there is a good performance as well. So indicating that training across various regions throughout the US is capable of performing well as in each individual area, at least for the central portions of the United States. And so we also have extreme events such as Hurricane Sally, which brought a large amount of precipitation to the southern coast of the US along the Gulf of Mexico. So the physically based 24-hour accumulation showed good results, with accumulations as high as almost 1 foot within a 24-hour period for the physically based results, and then for the machine learning results. And so opposite of the CNN, there tends to be a slight underestimate, but again, this is going to be because of the data constraints that we have, something that I will touch on in the conclusion slide in just a second. And so one last event is from the Western United States again. So as it was highlighted in the CNN results, there is generally poor radar coverage, which results in general underestimates in the precipitation. And so this is going to be a rather extreme case for this. And so this is going to be the 24-hour physically based result, whereas we can see the precipitation from the radars expand quite a bit with the machine learning based results. Although the correlation coefficient values do tend to not reflect this change, matching between the QPE versus the gauge values definitely shows a bit more improvement along the one-to-one line. And so in general, there were good results from both the CNN and LSTMs. And as was also mentioned within the MRMS network, we tend to have quite a lot of data available. Although one of the major issues and hurdles that we had to overcome was the fact that there's so much data available that we cannot get this into the model all at once. And so basically, there is a need for RAM upgrading or possible even storage. And so, for example, as was mentioned in the previous slides, there was only 18 days for training for Taiwan, which resulted in few cool season events and then very few typhoons, which tend to hit the area relatively frequently. So for a machine learning model potentially implemented in real time, this might potentially pose a few problems. And so there are only hours and days for the training for CONUS, but with the amount of data available, this needs to be increased for the vast, complex geography of the United States. And so one potential solution might be that of the cloud. So I'm running a little bit low on time, so I'll kind of just leave this conclusion slide for here with my email at the bottom. And thank you for listening, and we'll take any questions.